Hi students, myself Tanmoy Dotto, Assistant Professor, Department of Chemistry, JS College of Engineering. Welcome you all in the class of real gas. In previous class we discussed about the equation of the ideal gas, equation of state and real gas. Today we will discuss about the Amagat's experiment. There is a PV versus P curve. And from this curve we can determine the Boyle temperature. And Boyle temperature is very important for the liquefaction of the gas. Then we will discuss about the critical temperature, critical pressure and the critical volume. Molar heat capacity. There are two types of molar heat capacity. First one, molar heat capacity at constant volume and molar heat capacity at constant pressure, and the values of the Cp or Cv, there are different types of values for monoatomic gas, for diatomic gas, etc. etc. Then we will solve some numerical problems from the compressibility factor and the equation of state for real gas. So without further delay, let's start.
An ideal gas is one where there is no attraction or a repulsion force between the gas molecules. But if you think about the real gas, then that in case of real gas there is an attraction force between the or repulsion force between the gas molecules. So ideal gas, if you think about the ideal gas PV versus P, that graph will be parallel to the P axis. That means this is the curve for the ideal gas. This is the graph for the ideal gas. But a real gas deviates from the ideal gas, isn't it? Because there are two parameters, two factors which are not applicable for the real gas. First one is that there will be no attraction force, it is not applicable for the real gas. And second thing, there will be a fixed volume of the molecules in case of real gas. But in case of ideal gas, we assume that the volume of the gas molecules almost it is negligible with respect to the overall volume of the container. Now, depending on this fact, it is the Amagat's experiment, and according to Amagat's experiment, of what graph we obtained, PV versus P, this is in the slide. Okay, so that means that PV versus P, if it is the ideal gas, then it will be parallel with the P axis. Okay, this is the parallel with the P axis. But if it is not the ideal gas, then different kinds of nature of the graph we see here. Okay, from the Amagat's experiment. Maximum gases in the Amagat's experiment, most of the gases, PV decreases initially at first. Like this is the case of the nitrogen, PV decreases initially, but with increasing the pressure, PV increases. Okay, so here one example is such that nitrogen, that at first the PV value decreases with increasing the pressure, but after that, when P will be sufficiently large, the PV value for nitrogen gas is the large. Okay. And there are some gases in which case the PV value will be always higher than the ideal gas. Here the examples are H2 and the helium, hydrogen and helium. Okay, so for hydrogen and helium, this is their values are all PV values are always at any pressure. This will be always higher than the ideal gas. there will be some gases where the PV value will be always lower than the ideal gas. Here the example is the oxygen. For oxygen, look here, for any pressure the PV value will be always lower than the ideal gas. So the gases where there is a minima, and another case also there, that look here, in case of nitrogen, that with increasing the temperature, the depth, okay, this is the depth gradually decreases, isn't it? With increasing the temperature, the depth gradually decreases. So it is expected the minima, this is the minima actually, the minima, there will be some temperature, that minima will be vanished, okay, and it will be parallel with the ideal gas. Or more specifically, I can tell you that if you increase the temperature in such a way, okay, like 10 degrees C to 20 degrees C, okay, in this way, if you increase the temperature, there will be some temperature where this minima will mixed with the ideal gas, or the real gas behave like ideal gas. Okay, so it was also found that for the gases where there is a minima in the PV versus P curve, this is the minima, the depth of the minima decreases with increase in temperature at a sufficiently high temperature. What I told you, that with increasing the temperature, look, their depth is decreasing. Okay, so at a sufficiently high temperature, and it will coincide with the PV axis itself. When this occur, that means when this minima will meet with this here PV axis here actually, then what happened, PV versus P curve become parallel to the P axis over a certain range of the pressure, and the gas obeys the Boyle's law. When PV versus P curve, P value will be parallel to the P axis, then the gas obey Boyle's law. I already discussed with you what is the Boyle's law. Okay, so there will be a temperature when all the gases obey Boyle's law. So this particular temperature where the minima in the PV versus P curve coincide with the PV axis is called Boyle temperature. You have to keep in mind, because Boyle temperature come from this graph. Okay, so what is the Boyle temperature? Boyle temperature is the temperature when the minima of the PV versus P curve coincide with the PV axis. Okay, and thus each gas obeys Boyle's law at least one temperature over a certain range of pressure, isn't it? There will be a certain pressure where the each and every gas, there will be a certain pressure where the gas obey the Boyle's law, and this temperature is called actually Boyle temperature. However, you know, H2 and He may be looked upon as being always above the Boyle temperature if it is in the case of you know H2 and He, that always it will be above the Boyle temperature. Okay, and you know oxygen, it will be always in the below the Boyle temperature. Okay, so therefore we have to find out what is the Boyle temperature, or we can write down from this equation that a Boyle temperature is the temperature when this minima coincide here. So finally, when we consider the Boyle temperature, then T will be replaced by TB. Okay, so Boyle temperature, when we consider the Boyle temperature, T, we can replace the TB. It is the temperature of when all the real gas obey the ideal gas laws. So we can write down from the previous graph, you know, that Boyle temperature is the temperature when you know that delta PV, change of PV, delta PV divided by delta P, that at constant temperature, this is the Boyle temperature, that equals to 0. Okay, that equals to 0, you know. And you know that P is equal to from the real gas equation, P is equal to, we can write down RT by V minus B minus A by V square. I already discussed in the previous class that what will be the expression for the real gas, and from this expression we can write down P is equal to RT by V minus B minus A by V square, and from here we can write down that PV is equal to RTV by divided by V minus B minus A by V. Now we have to integrate this equation, this PV according to here. And after integration, what we'll get that TB is equal to, if you integrate it, you will get the value that TB is equal to, it will be TB is equal to A into V minus B square by RB into V square. Okay, and now at a very low pressure, that a volume will be sufficiently large, so we can consider that more or less V minus B minus B near equal to, it will be V. Okay, so then we can write down here that TB is equal to A by RB. Okay, so you have to keep in mind this equation. This is very, very important for numerical problem purpose. Okay, so TB is equal to A by RB. Okay, this is the expression for the Boyle temperature. Okay, this is the temperature where all the real gas obey the ideal gas equation. Now we'll discuss about the critical temperature, critical pressure, and the critical volume. Okay, so first of all, what is the critical temperature? So critical temperature, generally it is denoted by TC. Okay, critical temperature TC, critical pressure PC, and the critical volume, it will be VC. Okay, so critical temperature, it is the maximum temperature at which a gas can be liquefied, or the temperature above which gas cannot exist as a liquid. That means it is the temperature at which a gas can be liquefied, but above the critical temperature. Okay, so we consider that the liquefaction depends on the attraction force between the gas molecules. So attraction force will be very, very low above this temperature, so at that temperature the gas cannot be liquefied. Okay, so this temperature is called actually critical temperature. So you have to keep in mind the expression of the T. Okay, so it is actually TC. It is actually TC. So TC equal to 8A by, you have to keep in mind, this is very, very important, 8A by 27 RB. Okay, so this is very, very important, you have to keep in mind. So TC equal to 8A by 27 RB. So now come to the point, what is the critical pressure? Okay, what is the critical pressure? Critical pressure is the minimum pressure required to cause the liquefaction at TC. Okay, so you know that what I told, that TC is the temperature at which, okay, a gas can be liquefied. Okay, so at that time, what a minimum pressure required to liquefy the gas, this is called the critical pressure. Okay, so now if critical pressure PC equal to A by 27 B square, you know what is the A and B. I already discussed in the class of the when we discussed about the equation of the real gas. Then A is the pressure correction term and B is the volume correction term. Okay, so now it is the critical pressure. Now if we discuss about the critical volume, it is the volume occupied by 1 mole of gas at TC and PC. That means at critical temperature and critical pressure, what will be the volume of the gas? This is called the critical volume. Okay, and critical volume equal to Vc equal to 3b. Okay, so critical volume Vc equal to 3b. Now TC, VC and the PC, these three terms are very important. You have to keep in mind. And you know, if we try to find out that what will be the value of Z, that means compressibility factor, what will be the value of Z? So ZC equals to, you know, ZC equals to we can write down that ZC equals to PC VC divided by R TC, isn't it? So already discussed about that. Z equal to PV by RT. PV is the for real gas, and RT means it is the PV equal to nRT. From set there we get the RTC. So then if you put all the values means all the what you get, PC equal to TC equal to, then you will find out the value will be, just put all the expression, then you will find out the value will be, it will be 3 by 8. This is very important, you have to keep in mind. So here we will find out ZC, that means the compressibility factor at critical temperature, critical pressure and critical volume, it will be 3 by 8. Okay. So now come to the point that what is the molar heat capacity of ideal gas. You know, specific heat C of a substance is defined, already you know, in the thermodynamics chapter I discussed with you, that the amount of heat required to raise the temperature is defined as the amount of heat required to raise the temperature of the at 1 gram of substance by 1 degree C. This is called the specific heat capacity. Okay, if it is applicable for 1 mole gas, you know, this is called the molar heat capacity. So molar heat capacity means it is the amount of amount of heat required to raise the temperature. It is the amount of heat required to raise the temperature of 1 mole of gas to 1 degree C. This is called the molar heat capacity. Okay, so obviously we can write down that a molar heat capacity equal to specific heat of molecular weight of the gas. Okay, molecular weight, amount of 1 mole equals to molecular weight. Okay, so if we take the gas as the molecular weight amount, then we will get that it will be equal to the value will be equal to the molar heat capacity. So for gases where there are two values of molar heats, normally you know Cp and Cv. Okay, so molar heat capacity at constant pressure. Okay, molar heat capacity at constant pressure and molar heat capacity at constant volume. Okay, so Cp and Cv, there are two values are there. Molar heat capacity at constant pressure, it is taken as the Cp, and molar heat capacity at constant volume, it is taken as the Cv. Now for monoatomic gas, you know, for monoatomic gas Cp is equal to 5 calorie and Cv is equal to 3 calorie. Okay, so for monoatomic gas, you know that gamma is the Poisson's ratio, gamma is equal to Cp by Cv. Okay, gamma is equal to Cp by Cv, and you know that if you take the gamma, then Cp by Cv equal to 5 by 3. Okay, then Cp by Cv equal to 5 by 3. So if it is 5 by 3, then what will the value? 1.67. So you have to keep in mind that gamma is equal to, for monoatomic gases, gamma is equal to 1.67. Okay, how it is possible? Because Cp is equal to 5 calorie generally for the monoatomic gas, and Cv is equal to 3 calorie, and you know gamma is equal to Cp by Cv, and in this way we can write down that it is the 1.67. Okay, now for diatomic gases, you know Cp is equal to 7 and Cv is equal to 5 calorie. Okay, so just put the value, then gamma will be 1.40. so for diatomic gases gamma will be 1.40. for polyatomic gases, you know, for polyatomic gases Cp is equal to 8 and Cv is equal to 6. Okay, so gamma will be 8 by 6, 1.33. okay, so in this way you have to keep in mind that what will be the values of Cp and gamma, Cp, Cv, etc. for monoatomic gas, for diatomic gas, for your polyatomic gas, etc., etc. Okay, now come to the some numerical problems are there. Okay, so look the numerical problem. So it is the first problem that 1 mole of SO2 occupies a volume of 350 ml at 300 K 50 atmospheric pressure. Calculate the compressibility factor for the gas. Okay, so 1 mole of SO2 occupies a volume of 350 ml of at 300 K at 50 atmospheric pressure. Calculate the compressibility factor of the gas. How is it possible? You know, compressibility factor is equal to, I already discussed with you that compressibility factor equals to Z equals to you know that it will be PV divided by RT for 1 mole gas. If there is any mole, here it is 1 mole, so we can use this expression. Okay, so now you know P is equal to, look here, P is equal to 50 atmosphere. Okay, P is equal to 50 atmosphere. So just write down here P is equal to 50. So the value of P, it will be 50. Okay, now V is equal to 350 ml, but when we are calculating the liter the atmosphere, then we have to take the value in liter, not ml, because we have to put the value of R in liter atmosphere. So from that point of view, just you have to convert 350 ml to 0350 liter. Okay, so just you have to convert the unit. Okay, so 350 ml, we are converting the unit 350 ml to 0.350 liter. So V will be here 0.350. Okay, R, you know, for R is equal to N is equal to 1, R is equal to, here it is the universal gas constant, you know. So if it is universal gas constant, then it will be 0.22. Okay, so it will be 0.082, it will be 0.082 liter atmosphere Kelvin inverse mole inverse. Okay, so the value will be 0.082. then T is equal to, you know, what will be the T is equal to, what is the temperature, 300 K, it is given, so it will be 300. So this is the all the values are given here. Now what you have to do, you have to put these values, you have to put all these values in the equation. Okay, Z is equal to PV by RT. So now if we put the value, so Z equal to generally first of all 50 into 0.350 divided by 1 into 0.182 into 300, so it will be finally 0.711. Okay, so we'll get the value of Z equal to 0.711. So SO2 is more compressible than expected from the ideal behavior. This is very, very important fact. Okay, so if the compressibility factor is below 1, if the value of the compressibility factor is below 1, then it is more compressible. Okay, and if it is the greater than 1, okay, then we call it is the less compressible. So as because 1 is applicable when Z equal to 1, because PV equal to RT, then it is the ideal nature. Okay, ideal nature of the gas. So we should be careful about this fact. The question may arise in this way also, that predict either it is more compressible or less compressible from the ideal behavior or ideal gas. Okay, so then we have to check this value only, that either it is less than 1 or it is greater than 1. Okay. Okay, so now come to the second example. Okay, second example. So look here what is written. So in case of second example, 1 liter of a gas at 300 atmosphere. So look what values are given. 1 liter of a gas, first 300 atmosphere. Okay, so it is the pressure, and 473 K is compressed to a pressure 600 atmosphere and 273 K. Okay, so here two temperatures and two pressure values are already given. The compressibility factor found 1.072 and 1.375. Okay, very good. So for the two cases, compressibility factors are also given. The initial respectively at initial and final state. Calculate the final volume. We have to find out what will be the final volume. So for this purpose, what we have to do, so first of all, you know that we can write down that z1 in this way. There are two cases. So first case we are taking as the z1 equals to z1 equals to p1, for example, p1 v1 by rt1. We can write down in this way. Okay, so z1 equals to p1 v1 by rt1. We can write down in this way. So in the same way, we can write down that or here number of moles are given. So 1 liter of a gas. So here we have to consider the n also. So n also. Okay. So now if you consider this, then what happened, z2 equals to, in the same way you can write down that z2 equals to p2. So in the first case, look here, p1 v1 z1 nrt, okay, and then p2 v2 z2 nrt2. Then we can, from these two equations, we can write down that what will be the, from these two equations we can write down that what will be the v2, value of v2 equals to z2 by z1 into all the values you have to put, okay, 1 by 1. So then in this way you can find out that what will be the value of the final volume. Okay, so in this way, that means if you take generally z1 by z2 into z1 by z2, then what happens, this all the values you can get, all the values you can get, and you know all the values. Like if you take the p1 equals to 300 atmosphere, okay, then the volume is given here 1 liter, okay, so v1 equals to 1 liter, okay, we are calculating in a liter atmosphere, so no problem, no case of change of unit. Okay, so n is the what will be the value of n will be 1, okay, for the both cases n will be same, or whatever, n will be 1 or not, because the number of moles are same. So because one gas, there are different temperature, so it is not possible the change of the moles will be changed, it is not possible. So that's why in the both cases n will be same, so n will be cancelled out. Okay, then v1 1 liter, r, you know, it is the what will be the value of r in the r will be cancelled out. Okay, in the both cases r will be, when will be z1 by z2, n and r, these will be cancelled out. So only remaining part p1 v1 and the t1, and the second case p2 v2 t2. Okay, so p1 v1, you know, t1 is the 473k in the first case. In the second case p2, what will the p2 will be 600 atmosphere, v2 you have to calculate, and t2 is the 273k. So this is very simple, and the answer will be 370 ml. Okay, so just in this way there may be some kinds of questions where you have to find out in this way, where all the values are given, only you have to find out the v2. Now come to the next question, that calculate the van der Waals constant for ethylene. Okay, so in this type of question, I told you that you have to keep in mind what was the expression of PC and TC and VC. Okay, so if you keep in mind these three expressions, then only it is possible to calculate that what will be the van der Waals constant for a particular gas. I will show you that what are the values of the three cases, PC, VC and the TC. So look here, that here in this case, so in this case look here, that TC equal to 8a by 27 RB, PC equal to a by 27b square, and VC equal to 3b. Okay, so these three values you have to keep in mind. Then you can calculate, just put here one by one value, like here b is equal to 1 by 8 r TC divided by PC. Okay, so in this way you can find out either PC by TC or VC by TC, such a way that you can get one value, either B or A. So in such a way you have to place these values. Okay, so B is equal to, look here, that 1 by 8 R TC by PC. So just put here the values, R you know, and TC you know, whatever the value TC, it is given that it is the 282.8 and PC this is the 50 atmosphere. So these all are given here, just you have to find out the value of the B. In the same way, if you try to find out the value of A, so look here, that A is equal to 27 by 64 R square T square C divided by PC. So here also same case, TC and PC are given, so you have to replace actually what is the aim of this type of, to solve this type of problems, that VC value is not available. Okay, so just what you can do from these two equations, just arrange the equation in this way, there will be no VC. Okay, there will be no VC, okay, because only TC and PC values are given. So in this way you can find out that A and B, that means A value will be here 4.47 and here B value will be 0.0557 liter per mole. Okay, so this way you have to solve so many problems, because from this chapter, from the real gas chapter, there are so many types of questions. In the another class also I have discussed with different kinds of problems where there you have to apply some equations of the Van der Waals equations, but here Van der Waals equation is not required, but here it is very much required that you have to find out the A and B value, that the A and B means the pressure correction term and the volume correction term from the critical temperature, critical pressure and the critical volume from these equations. Okay, so another way is the compressibility factor. You have to use the compressibility factor also, and there from there you can find out the different kinds, you can able to solve different kinds of problems. Okay, so that's all for the real gas chapter, and you know that to understand properly real gas chapter, you have to know the characteristics of the ideal gas. That's why at first I started with the ideal gas, concept of ideal gas, equation of state and the ideal gas equation, and then why real gas deviate from the ideal gas and ideal gas behavior. Okay, so in this way, so that's all for today, and just start to read the chapter and start to solve different kinds of problems from any standard book. Okay, and meet with you in the next class with a different topic. Thank you, thanks for watching, goodbye, take care.